Okay, this week I decided to do a little presentation on fuel trim and some of the stuff that's related to it. Fuel trim used to be called block learn and integrator. In other words, block learn used to be long fuel trim back in the day. They didn't call it that, but they call it block learn. And what we call short fuel trim these days used to be integrator. Now that goes way back a long time ago. But the simple fact is that the integrator and the block learn back in those days and the short fuel trim, the long fuel trim, you cannot measure those anyway except with a scan tool. You have to have a window into the computer's thought process before you can come up with what it is that those things mean. Alright, now this right here, some of the earliest fuel injection systems I got involved with, this is a Nippon Denso. It was on an 85 Toyota vane air meter. Now on this spring-loaded flap right here, it's got a calibrated spring. There's an L-shaped flapper that air goes through that's underneath all this, and that L-shaped flapper is connected to this wiper, and as the air comes in it goes this way. You might notice this little rod right here has got these points. There's a set of points right there, and those points actually drive the fuel pump. So when you start spinning it over, this moves just enough to let those points close. The fuel pump kicks on, and then you're basically getting, this is like a throttle position sensor, only it's measuring airflow. They call this L-jetronic because the vane was shaped like an L, presumably. But anyway, that I had pulled the top off this. As a matter of fact, somebody had already pulled the top off of it, and it was real easy to get it off, so I just managed to lift it off of there. And it was on a Toyota that we were working on that had a strange idle problem. And according to the measurements I got on this and the Toyota book, this wasn't reading right, but whenever I checked to see how much it cost, and this has been 20 years ago, one of these things right here, if you wanted to buy one from Toyota, was $800. And so I said, well, we didn't need to buy that, and we found a problem somewhere else. But if you just went by the numbers based on what your shop manual said, we would have replaced this. But we found out it was a coolant flow problem through the idle air control valve, which, the Japanese Asian vehicles for years, and some of them still do, I don't know, they enjoyed using hot coolant to go through there and operate on a wax pellet along with an electrical circuit for your idle air control, which makes for like a $500 idle air control unit, but anyway. But this slider, as it goes up, is going to increase the voltage, and that's going to, help you with your fuel injection and all that. The set of points that provide power to the fuel pump, once again, are right there. So if you're going to unplug this and run the vehicle, you're going to have to bypass the two terminals that, you got to jump power to the fuel pump by bypassing. I don't remember which terminal these were, and how this little code is. You got to have the book in front of you before you'll know what each one of those means. Now this is a diagram of K-jetronic fuel injection, and it uses airflow to regulate fuel. It's totally a mechanical system, and it's initially when it came out was in the late 70s, as I remember, on the Volkswagens, and I was working at the dealer on these. And DeLoreans have this kind of system on them too. In case you're ever wondering what a DeLorean has for a fuel system, it's like this. And this fuel distributor right here, if you ever take one of those fuel distributors apart and put it back together, you're never going to get it to seal up or work right or anything. Those things are assembled in a laboratory, and I'm telling you, the tolerances are in microns. It's just incredible. And those little slits in this little tube that valve slides up and down in have got to be cut with a laser. I don't know how else they're going to cut them. But the simple fact is, this plate right here, there's a little piston, that little piston sitting on this plate. And as the air comes in and raises that plate, it raises that piston, and that sends more fuel out. These little atomizers, are pretty cool. See the big fat O-ring on there? They just snap into a little plastic piece that's screwed into the head right there. And it's real easy to pop them out of there and snap them back in and put a little motor oil on the O-ring. But they will actually, that O-ring keeps it from having a vacuum leak and all that, but it also just, anytime, you could actually pull those out and put each one of them in a bottle and operate that fuel distributor with a fuel pump running, and you could watch the fuel. It's a constant mist. It doesn't pop them like your old GM system with the poppets did. There was a little adjustment right here, the adjustment screw. What we would have to do on the Volkswagens is there was one little port over there on the exhaust where you would connect an exhaust gas analyzer to, and you would turn that screw. Well, nope, I got that crossed up with the one that's got the vane airflow meter on it. Scratch that from your head. The one with the vane airflow meter in it, you would have to do adjustments on the vane airflow meter until you were reading 1% carbon monoxide, which just sounds like a lot, but back in those days it wasn't all that much by the spec. But this little mixture screw right here, you'd pop a little plug out, and when you pop that little plug out, you would basically, it usually was an Allen, they show a screw there, but it was an Allen, and it's right here. See that? It goes down in there. So anyhow, that's how that kind of thing worked. And I kind of enjoyed working on those. They were a lot of fun. This is the way they were wired up. They had a warm-up regulator, which was basically a bimetal thing that let more fuel. Well, you see how this fuel is going in on top of that piston? Well, whenever the warm-up regulator was cool, it would basically have lower pressure going to counteract the upward motion of that piston as raised by that plate. And that would let it run a little richer. As it warmed up, it would increase that pressure so it would, counteract. It's almost like in a transmission, line pressure or governor pressure push back and forth against each other. It's kind of like that. And that's why you see that warm-up regulator like that. But you got an auxiliary air regulator that's made in a very similar fashion, and it basically would let extra air go around the throttle plate when the engine was cold until that little bimetal strip warmed up and it closed that off. That seemed awfully mysterious to me until I got a little training on it. Here's your cold start injector, which is there for that extra fuel that I was talking about a couple of weeks ago that you need for your cold start, which it does the same job that the accelerator pump used to do. That was before they figured out that they could, put extra fuel in there in other ways. And a lot of vehicles had a cold start injector, make it start better. And there's your little atomizers coming out of the fuel distributor. So this came in, it raised that up, and it pushed that little piston up, and it let more fuel go through those metal lines. And those were braided metal lines too. They're really made well. Now you had a pressure reservoir here, which was kind of like an accumulator, and a fuel pump. And you notice how they like to feed that fuel pump with gravity. They put it down low so it can be gravity fed from the tank and all that. And then there's your fuel distributor is right here, and that's what I was showing in that other slide earlier, which was that thing right there. All right, now today's mass airflow strategy. Mass airflow has priority on this particular system. The MAF system doesn't need to know anything about throttle position, exhaust gas recirculation, EGR flow, or any of that. It's just basically reading air. That's its priority. And these mass airflow sensors work several different ways. I always enjoyed reading the voltage on the Ford ones, but the GM ones would produce a hertz reading, and you could basically look at that. I had one white box mass airflow sensor I put on a Chevrolet, and in spite of the fact that the hertz was reading properly, I wound up having to get a Delco brand and put on it because it kept throwing a code. In spite of the fact that if you looked at it with your meter reading hertz, everything seemed like it was just like it was supposed to be. These two wires right here, this is a dirty one I took a picture of. If these things get dirty so that they can't respond quick enough to that air, you're going to have a sluggish acceleration. I've had vehicles come in and they said, hey, it's not accelerated right, and I would just spray that and clean it off, and it would, everything would be crisp again. A lot of people clean those. The thing about it is they shouldn't get dirty if you're changing your air filter regularly, because the air filter filters the air that's going across these, and if there's crud on those, there's something getting past the air filter, and that indicates the problem right there. Now they got a cold wire that keeps track of the ambient temperature, and a hot wire. The temperature heats above that ambient temperature to maintain a constant temperature above the temperature of the cold wire. Usually it's 300 degrees Celsius or something like that. And the mass airflow signal is calculated based on how much current it takes to maintain the temperature differential between the cold and the hot wires. And there's a whole bunch of different ways they look, but that's just one of them. And some of your diesels now have got mass airflow sensors on them like that too. This system can use other inputs to infer mass airflow if the mass airflow is disconnected, but I've seen shorted mass airflow sensors completely shut the system down where you'd have a no start because of the mass airflow. Now they need power. If something else fed by the same fuse causes that fuse to blow, you'll get a mass airflow code on your scan tool, but that doesn't mean that you need to throw a mass airflow sensor at it. Case in point, we had this Chevrolet pickup, had mass airflow on it, had a mass airflow code on it, and we replaced the fuse, pop, as soon as you turn it on. Now there's power, going to the 12 volt power going to the mass airflow sensor. And so I put my little circuit breaker on there with this, with the light bulb wired, parallel to the circuit breaker, and it would go ding 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 ding. And whenever we would unplug in everything we found that was fed by that, when we got to the oxygen sensor, the downstream oxygen sensor on the on bank number 2, which was on that Chevrolet, was the right hand bank. We basically, our short went away, and so it turned out we had a shorted out oxygen sensor that blew the fuse. The oxygen sensor heater, actually. It blew the fuse, but we were getting a code for a mass airflow sensor, so don't fall in a trap like that. Just because you're getting the fuse blown. If you've unplugged the mass airflow sensor and it still blows the fuse, and you looked at your wires, you need to start unplugging other components. I always like to do the easy thing first, but we wound up putting an oxygen sensor on that one to fix the mass airflow sensor code. Check for good voltage at the mass airflow connector if you get a code for a dead MAF sensor, and or check the fuse in question. This is basically, this is a very simplified schematic I put together of that. Ignition voltage, mass airflow signal. This is coming in, and ground's coming in from the bottom. That's really the way I think that ought to be drawn. Now, unmetered air leaks, that refers to any air that enters the engine without first passing through the mass airflow sensor, like we do here. We talked about that last week on one. The PCM figures fuel delivery based on mass airflow readings. Any air that goes in there that's not going through the mass airflow sensor is going to cause it to put not enough fuel in there, and your fuel trim readings are going to go positive. And so it's going to be an out of balance fuel mix because it's going to pick it up as a lean condition. So basically, that's why your fuel trims will go to the plus side of the zero when you're looking at your fuel trims. It'll start out, the short fuel trim will go first, and then the long fuel trim will follow it. If the short fuel trim kind of maxes out, the long fuel trim keeps going up. A lot of times, though, if you go in there, you'll see the short fuel trim on 0 and the long fuel trim at like 28% or something like that. That means the long fuel trim has adaptive learned to the point that it has the short fuel trim back on 0 again, that's what its desire is, to keep that thing is running really clean, even though it's having to twist it way out of balance to keep it there. Anyway, pay attention to these things right here and other leaks that are between the mass airflow and the throttle body. Any air that's getting in there that's not being run through that mass airflow meter is going to cause a problem in the way of your fuel trims. Now they'll climb with that when the unmetered air leaks are present. It's like that. You hold the throttle open a bit when there's an unmetered air leak, and that drives them back toward normal usually. It's a good piece of data to pay attention to. Now, the PCM can only change the amount of fuel in the mix. The incoming air may be altered by a clogged filter, but on some of them, like on some Lincolns, and this was on a Lexus SC300, whenever you start spinning the wheel, their traction control system, you can barely see it. This is a throttle plate down on the bottom that you're opening whenever you open the throttle with your foot. If you got that thing spinning its wheels and the electronics pick up on that, this throttle plate you see right here that's looking straight at you, you can't, I should have had it turned where you can see it. That throttle plate will begin to close off and stop your airflow, or it regulates your airflow automatically so you're not spinning the wheels too much and that kind of thing. It controls fuel based on its mass airflow measurement of the air entering the engine, though. But that right there is something that I thought was very interesting, that Lincoln and Lexus both do that. If you guys know of another one that does that, let me know. Those are the only two I personally experienced that have that secondary throttle plate up there that closes it off if you're, doing something naughty. All right. Why do fuel trims go positive when the oil filler cap is removed with the engine running? So if you pull that oil filler cap off with the engine running and you happen to be watching your fuel trims, you're going to see those fuel trims immediately start to climb. Now the reason the fuel trims immediately start to climb is it starts to read lean because the PCV system is pulling air out of the crankcase all the time, right? Well, if you notice, the little closure hose is downstream of the mass airflow sensor, and it's going to let air, the air that goes through the mass airflow sensor is filtered and clean because it's already gone through the air filter. See, this one doesn't have a crankcase filter per se. It uses the air filter for the crankcase filter, which is really smart. And it goes right down and it pulls that air through the crankcase to get rid of the blow-by from the piston rings and out into the intake plenum, and then it processes it. PCV system is the oldest emission control that I know of, and it first appeared in the early 60s on Corvairs. Okay, now this situation here is because when you take that oil filter cap off like this, air is going to be coming in there. The PCV system is going to be pulling air through the oil cap, and that's going to cause the fuel trim to climb. So here's something you need to consider. If you've got an oil filler cap that's got a damaged seal under it so that air can leak past it, or sometimes you'll see one that the seal has just come off of it and people feel like, well, if oil's not going to splatter out of there, I can just screw it back on there and be aight. I've actually seen some of them that if you leave the oil filler cap off, it will throw all the, you know, the way the thing is designed on some screwball engines. If somebody fools around and leaves the oil filler cap off by accident, it will throw every last bit of the oil out of there and lock the engine up. That doesn't happen on very many platforms, but I've seen a couple of them that will do that. Speed density system is the weight of the air is calculated on this kind of system using the manifold absolute pressure sensor, MAP sensor they call it, but it requires the PCM to do more mathematical calculations than the mass airflow, which is a simpler way to measure the weight of the incoming air. Now these are all factored in on MAP sensor dominant vehicles: engine RPM, engine volume, throttle plate position, manifold absolute pressure, intake air temperature, and barometric pressure. Now, engine engine coolant temperature is not listed here, but it's factored in too, and I fooled around and didn't put that as one of my bullet points. But the thing about it is, intake air and engine coolant are always going to be factored in anytime you're running the engine on any of them, mass airflow or MAP. Okay, so they're always going to modify the pulse width. Barometric pressure will always modify the pulse width. Throttle position and how fast you're opening the throttle will have something to do with that too. Engine volume means engine displacement. You know, it's volumetric efficiency. Like your 3-liter engine is supposed to, if you turn the crankshaft 2 turns, you're supposedly moving 3 liters of air through there, but that's not the way it is because the air's got to make so many curves going through there that your volumetric efficiency is not going to be 100% unless you're running a supercharger or a turbocharger. Of course, RPM got something to do with it too. Unregulated fuel sources, which is dripping injector, saturated carbon canister, high fuel pressure, ruptured fuel pressure regulator diaphragm. That's what I meant to say, regulator right there. If you pull that hose off that fuel pressure regulator and there's fuel in it, that diaphragm is ruptured, and if that gets bad enough, it can actually hydraulic lock a cylinder. If enough fuel pressure keeps trickling in there, like on a hot day, you've parked it, fuel starts going into the intake manifold, there's a valve, an intake valve open, it starts dripping fuel in there, and if it gets enough fuel in there, you can, and I've actually seen this happen before too, an engine was destroyed because this little diaphragm busted and it leaked in there. And of course, if you got a saturated carbon canister, you know, because somebody packing the gas or whatever like that, it's also going to make it run rich. Dripping fuel injectors will typically be more likely to cause a hard start problem than they will a rich running problem. If you've got engine oil that's contaminated with fuel, it's going to be pulling through the PCV system. It's going to pull fuel vapors, and that's going to skew your fuel trims. One of the things they used to tell us in the very old days on Fords was, if you have one that's reading rich, well, the first thing they want you to do is pull the PCV valve out of there and put a piece of paper over it. You put that piece of paper over the PCV valve. If the fuel trim normalizes, that means that you need to change the oil before you do anything else. Because sometimes you have enough fuel contamination. Even if there's nothing else wrong with the vehicle, if you have gone a long time without an oil change, a lot more than you should have, you're going to have fuel contaminated oil. Basically, it's going to depend on the driving habits of the person that's driving the car and all that. But it's really kind of crazy to throw a bunch of parts at one when an oil change would have straightened it out. See, because a lot of times you're looking for a reason for a check engine light code whenever you're doing this anyway. All right, short fuel trim is an instantaneous fuel pulse width adjustment to what the O2 sensors are telling the PCM. The long-term fuel trim is the adaptive memory part of the picture, and follows short fuel trim, which makes course, in other words, the long fuel trim makes course adjustments for the fuel delivery when short fuel trim, which is instantaneous, wobbles too far out of line. If short fuel trim goes up, and it's going up too fast, and it can't correct the concern, the oxygen sensors are still reading what they were, then the long fuel trim starts to ratchet it up in steps, and it happens a lot slower. Look at all of this, these different PIDs on that. There's your intake air temperature. The throttle position is a percentage. Grams per second is what you're reading on your mass airflow. Incidentally, if you want a little trivia there, the displacement of the engine is going to be usually very close to, it's going to correlate very closely with the grams per second reading that you get. Like if you've got a 3.8 liter engine, typically your grams per second at idle is going to wind up being real close to a number that's similar to your engine, your displacement of your engine. See, this one right here, you might notice is basically got mass airflow and map. See that? Now, what you're looking at with map, a lot of the times you'll read on the scan tool, it'll say intake manifold vacuum and manifold absolute pressure. Now, manifold absolute pressure, when you add it to the intake vacuum reading, is going to give you a figure that's equal to barometric pressure. So barometric pressure, the barometric pressure number is divided between manifold absolute pressure and vacuum because they're two sides of that same coin. It's a seesaw. Short fuel trim here, you notice short fuel trim 1, this is like a 2-bank engine. Long fuel trim, see how this is really close to 0? This is like it's supposed to be running. That one's just below, this one's just above, this one is just above, that one just below. Notice how they're both floating along there together. There's your RPM, that's a little more than idle. You've got just a little bit. Your closed loop fuel control is important too, because if it's not paying attention to the oxygen sensors, then your fuel trims are going to be figured by something other than the oxygen sensor. We're driving 42 miles an hour here too. Seems park advanced at 15 degrees. All right, let's see. That's about all I got to talk about there. Engine coolant, you notice, is 177 and intake air temperature at 59, which is what you expect in a normal situation. You won't always see the problem with a scan tool. Now, there's a lot of people that like to spend a lot of time enjoying the cool AC with the engine running, sitting in the car, pretending to look at the scan tool screen. There's only so much you can figure out that way, and pretending to work on the car while playing on your phone is not helping either. I used to have to tell my students about that. There's an exhaust restriction downstream of the catalyst, like an internally damaged muffler with a baffle blocking its outlet, so the engine can't breathe out. Can we find that with a scan tool? What do you think? Alvin Moore, he writes for Motor Age, just like I did, has done a study on that. All right, so he put a man-made exhaust restriction in place on his Ranger, and at wide open throttle, looking at that line, there's your wide open throttle. It didn't have a lot of power, which you could feel that, but you really couldn't see it here. The only thing he could see here that was any different than when he didn't have a restriction was that there was a 74% reading on your load rather than 95%. That's the only difference that he saw. All right. Now, even though this Envoy, which is Envoy, he bugged this Envoy, this GMC Envoy, the same way, it was struggling to maintain 60 miles per hour. The data PID showed nothing out of the ordinary. Just looking at your data, you could not look at your data PID on these and tell that it had a clogged exhaust. All right, look at that one right there. See that? When he went wide open throttle on this one, you might notice his oxygen sensor, it went full rich because it knew he was wanting wide open throttle. Now this right here is the one that's behind the catalytic converter. See, it's lazier. All right, now this right here is your long-term fuel trim. You notice it's kind of bobbling along there, that just above 0. And that one there too, your short fuel trim. Look at those. All right, and you might notice he actually got a transmission shift out of this. When you see this, This is a transmission shift. That's how that was. He went on up through there, and then he let off, and he let it come back down. See, he basically was coasting, and then he came back down to speed. But the simple fact is, if you think you're going to sit there and look at a scan tool screen and tell everybody exactly what's wrong with it, now Mac Vandenbrink, whenever he was teaching his scope classes, he could show you how to find a rounded off camshaft lobe looking at the ignition pattern. And that's really some high-end stuff. But here, by the way, his engine load was 99% on this one, and the map was reading at 28.6. The manifold absolute pressure was real close to barometric pressure because he was just pushing it all the way down. The smartest thing to do, though, if you're fooling with a scan tool or scope or anything else, is get used to what normal patterns look like and get those in your mind so you know exactly how they're supposed to look. You might even store some patterns you can go back and make reference to. If you're just looking at squiggly lines on a screen, I found that out when I started using the Service Bay Diagnostic system back in the early 90s. If you're just looking at the screen and you're saying, well, what am I seeing here? I mean, I see lines and I see what's happening, but I don't know how it looks and when it's a normal car. One time there was this Contour, this Ford Contour that I was looking at that had a sort of a harsh transmission shift. And so I made a recording and I said, yeah, I see these lines on the screen. But I took the flat recorder and I plugged it into another one that was just like it could do that a lot of times at the dealer because you got two cars just alike. And I plugged it in over there and I drove that one and made recordings on that one and brought it back, uploaded that to the Service Bay Diagnostic system, and I compared the two graphs and saw what the problem was because I had a good graph and I had a bad graph. See, that's really important. That's why so many of your databases have good and bad cam and crank sensor patterns and all that. Making a vacuum leak. It's wise to get accustomed to what the scan tool data looks like when there's a vacuum leak, and the effect is obviously slightly different on mass airflow systems than on manifold absolute pressure systems. Now, this blue line is placed at the point where a vacuum leak was introduced. Now look at this. As soon as he introduces a vacuum leak, what did the oxygen sensor do? It bailed all the way to the bottom. And then it recovered because the short fuel trim started ratcheting up really fast. Now the short fuel trim went up there and stayed up long enough where the long fuel trim started taking action to bring the short fuel trim back to zero, which is what it's always trying to do. And that's pretty much what it enabled. I mean, what it was able to do. So it was able to bring it back. Now you notice that oxygen sensor did the same thing that one did. And this fuel trim here did the same thing. Both the fuel trims look pretty much the same because the vacuum leak was common to both banks. Now if you had a vacuum leak just on one bank, that's something else. I will tell you, if you have, for example, I had seen a Mustang one time that this mechanic put back together after he had the heads off, and it was a 4.6, I think, and a saline or something. He had the valve timing slightly, one tooth advanced on one side. What he was reading with his fuel trims was his left bank was reading plus 10 on the fuel trims, and his right bank was reading 10 minus. Because of the way he had timed the camshafts out. So whenever he put the camshaft timing back like it was supposed to be, they both balanced out. That was kind of an interesting thing. And that was not one with variable cam timing either, by the way. That was one of the older ones. Now the vacuum leak created on the Envoy is so that the PCM, notice what the PCM did with the vacuum leak is going to cause it to idle faster typically on a fuel injected engine unless it's a really horribly big vacuum leak right close to one runner, and if it's common to the whole plenum, you're going to get a faster idle. All right, the engine controller didn't like that. It closed the electronic throttle body. See that? How that TPS is actually on the electronic throttle body on this one, and it went down. RPM basically was doing wacky stuff. Now if the electronic throttle body closes but the RPM stays up, a lot of these platforms will turn the injectors off because they're trying to protect the driver from one running away. All right, you notice how that oxygen sensor 2 went down when he made the vacuum leak. It did this and all that, but this is all related to, there's other things going on, there's other dynamics, and that's the point. There's your long-term fuel trim. It's at -2. Short-term fuel trim is waggling around here. And then you can look at that. You can just analyze these little graphs. It's always a good idea to see what's going to happen when you do one thing or another, just so you can understand how it's thinking. Now, back in the mid-80s, Buick, as I remember, came out with both coil pack ignition, which is the first time that I had ever seen that on a car. Motorcycles had something similar to it, where it was firing the plug on the intake and the exhaust stroke. But they came out with mass airflow, and they also came out with coil pack ignition on the same vehicle. And this thing wasn't quite perfected enough, and they would start giving trouble. And the diagnostic on those mid-80s Buicks was, if you whacked this thing with something like a screwdriver handle and it, bucked and jumped and didn't run right, you were supposed to replace this. And they also had a technical service bulletin where they had you add a map sensor so that it would have that as a backup input in case it needed it. And so that was kind of like in the early years of the Vietnam War. They felt like they didn't need guns on fighter jets anymore. They just needed missiles. And the fighter pilot said, this is a bunch of hogwash, because if you shoot a plane down with a missile and you're too close to it, you're going to kill yourself too. And so they mounted these big 50 caliber machine guns under the wings on those F4s, and they made them where they would just dance around loose, but they were, pointing ahead. If you mounted them solidly, they'd rip themselves off the wing. And this old fighter pilot that flew those things told me that you couldn't see. There was no gun sight. You just had to point your plane at whoever you were chasing, whatever enemy plane you were chasing, and whenever you pulled the trigger on those machine guns they mounted under the wings, they would just waggle around, spraying bullets around out there everywhere, and you hope you were going to hit him. But anyway, many platforms today, though, have map and mass airflow sensors, and Chrysler products, though, used only map sensors to stay away from mass airflow for decades, except the ones that they did in conjunction with Mitsubishi. And those Mitsubishi mass airflow sensors were downright weird. They were super expensive, but they had some of them had a little speaker on one side of the air. The air is blowing between this two. They had a little detector, and they had a speaker, and the sound that was being generated, it was ultrasonic, you couldn't hear it, was basically picked up by the speaker on the other side. And so the more air that went through there, the more that sound was deflected. And it was a sonic mass airflow sensor, and that was something you would probably see in like a 92 or a 93 Eagle Summit, or something like that. Yeah. All right, anyway, that's the map is a good way to check for EGR activity. What happens to intake manifold vacuum when you open your EGR, vacuum drops? Also, your oxygen sensor, GM used to use the oxygen sensor for feedback to see if the EGR was flowing right, because your oxygen sensor is going to do what? Whenever you displace some of the oxygen with inert gas from the exhaust system coming through the EGR and into the mix, you're basically going to see the oxygen sensor drift up a little bit. That's just the way that kind of works. But it can also be used as a backup default in case of mass airflow failure. Now this got to where it was fairly common beginning in the late 90s. Altitude issues in atmosphere: 21% oxygen, 1% inert gases, 78% nitrogen. Now these percentages don't change with altitude, but what does change is air pressure. Now you look at this: in New York, 14.7, right down there at sea level. St. Louis is at 600 feet, that's at 14.4 psi. Denver's at 5,000. Water boils at 160 degrees in Denver, from what I heard. And way up here at Pikes Peak, which is 3 miles up, it's 8.6 psi. No wonder it's hard to breathe up there, right? Now the engine needs air pressure differential to breathe. So as the piston's going down, it creates low pressure and the air rushes in to fill it and all that. A turbo might adapt to that change, but it's still affected. Modern EFI systems only add and subtract fuel to maintain a 14.7 to 1 air fuel ratio. They can't change pressure coming into the engine. That's why engines lose power proportionally with altitude. In 1972, well, no, it wasn't in 72, I'm sorry, it was later in the 70s. I had a 72 Chevrolet, and I went on a trip out there to the Grand Canyon on that 72 Chevrolet, and the rim of the Grand Canyon is about 8,000 feet above sea level, And the farther we got into Arizona and the higher that altitude got, the worse that car ran. Now, if you want to make adjustments to make it run better, you can basically advance the timing and do some carburetor adjustments, because whenever you don't have as much air, you need more time for the mix to burn, right? So changing the time, advancing the timing and adjusting the carburetor is what you had to do to get one ready for altitude. Now, fuel injection can handle up to 4,000 feet altitude usually without any special modifications. There may be some now that can handle it all the way up, I don't know. In the olden days, we used to have if you were going to altitude on something like a Jeep CJ, they had a little wire that you were supposed to ground. It was a ground that was hanging there that was taped off, and as I remember right, it was black with a white stripe or something like that, and it was an altitude modification wire. Now, the Jeep Cherokees that had that crank sensor back there, you know, with the two ears on it, you remember. I ain't talking about the one that takes a little paper spacer. I'm talking about the one that's got the two ears on it, like on a Jeep 4-liter. For altitude modifications, you had to put a different crank sensor on there, and it was actually in a different indexed spot on the crank, on the flywheel, so you would have about 8 degrees extra time in advance, even, you know, at static timing. So anyway, that's just all that stuff you got to do. Mass airflow sensor on non-mapped equipped cars infers barometric pressure with calculations. Now, the barometric pressure is calculated by the map sensor. When you switch it on, barometric pressure calculates map. I mean, the map sensor calculates barometric pressure. This is the Ford one that reads hertz. You know, there's your old GM one that reads volts, and now that's your mass airflow there. That one there, and this one right here, that may be a map sensor too. But you know, they come all different kind of ways. Some of them are fed with hoses. Some of them go right into the intake. But the point is, when you switch the key on, you're basically going to get barometric pressure on the way to the start position, and it doesn't take it but a second to pick up on that. When you're going wide open throttle going up a hill, it's going to update that barometric pressure reading so it can make more accurate calculations. Older Fords, this right here, whenever you were at sea level, if you took a meter that read hertz, if you went into that signal wire coming out, you know, of course they had just 3 wires going there, the signal coming out didn't read voltage, it read hertz. And so when you poke that thing in there, you're supposed to read about 158 to 159 hertz at sea level with normal air pressure, and there's no hurricane out there or whatever. And of course, you know, you need a barometer so you can tell what the local barometric pressure is too, but you can get that on your phone nowadays if you pull up an app. But when you cranked it up, it would be about 110 hertz. And so that was pretty good. If that vacuum line was off, you would be reading 158 hertz all the time. It would run rich as a dog. Sometimes the vacuum line going to that would be clogged up, or would have some jelly in it that got sucked out of this thing, you know, all those. And there's a lot of little problem things you could talk about, map sensors and all that. But so when the map sensor barrel reading fails, it usually reflects a higher altitude, usually. You know, not every time, but this drives the fuel trims which way. If you find a fuel trim related problem you think you fixed it, I'm going to tell you a little story in a minute that's going to answer that question I just asked. If you find a fuel trim related concern, you think you fixed it, do a fuel trim reset with a scan tool or by disconnecting the battery, restart it, and watch for closed loop. When it closes the loop, if the short fuel trim stay close to 0, you fixed your problem. If they start walking really fast, you got more work to do. Now, this guy had fuel trim that was plus 27. It was adding that much. It tossed it. He threw an O2 sensor at it, did a battery reset, and went right back to 27, just like I was talking about. Barometric pressure pid was reading 24 inches. We're at near sea level, so it should have been reading close to 30. Barrel readings will change when a storm is there because of pressure changes. And the fix was to replace the map sensor, which took care of the whole problem. That was something I saw when I went over helping my buddy one day. Anyway, that's all I got for you today. I hope I hadn't bored you to tears, and I'll be happy to see you guys next week. Give me some feedback on this thing. Let me know if it helped you.